So the name of this exercise is What's Your Worst Idea? Martin, can I tell you my worst idea?
I'd love to hear your worst idea.
I mean,
And
I'm gonna
please make it really bad.
okay, I'm gonna save my best ideas for other times, but I feel comfortable to share my worst ideas with you. We've recently published a model where cells are able to transition from state to state, where this is a more like adaptive state. And so in a sense, they've learned that state. It's adaptive to this new situation that they find themselves in, for which they have no program, which is that there's a drug. Okay, so there's some drug, they don't know that drug, and they have to adapt to it. Okay, they have the solution, they have aspects of the solution, like they have all these genes, all these pathways. They just have to realize which ones to turn on. So, in other words, they don't have the input for turning on the right genes.
But you're not talking about Darwinian evolution here.
It's not Darwinian evolution. It's like exploration, it's improvisation, much like what we're doing here. And so the mechanism is that there are these dimers. And the dimers are of the family AP1. It doesn't matter. There's 19 different kinds of subunits. Like the famous ones are June and Phos, but there's 17 other ones. Okay. And they dimerize.
Okay.
And so a crucial part of this model is that the cells find the right combination, the right AP1 pool. So maybe this is June D Phos L1 as a dimer. This is June B Phos L2 as a dimer. And so there's one particular AP1 pool. Maybe this is June Phos. And then here, there'll be like, maybe this is June ATF4 and Phos Math F. And
Well, can we just call them ABC?
Exactly. That's even easier. So this could be like AB, CB, and then, but it needs to find the right one.
Okay.
So now I've been asking myself, what's the killer experiment? Like how to test this?
Yes.
And recently, I've been in contact with a researcher from San Diego. His name is Alon Goren, and he has a method that can actually tell you which of a set of dimers that you pre-establish, you say ahead of time which proteins you're interested in, and it will read out for you whether they dimerize or not. Okay, so
what does that mean, whether they dimerize?
whether they're in close proximity to one another. So let's say,
So he can map the pool. That's what he's saying.
yeah, he can map the pool essentially.
Okay.
I now have a technology where, not on the level of an individual cell, but of an entire population of cells. So that's a problem,
Okay.
right?
Well, but you will assume that the whole population adapts in a similar way, or not?
I don't know if I can actually make that assumption, but
Okay.
I would assume that that once a good combination is found by one of them, it will do very well and out-compete other cells.
So these cells are replicating?
Yeah,
Okay.
they're not going to replicate themselves.
Well, I mean, you didn't tell me what kind of cells you're talking about.
Yeah.
Like, if those are the cells in my lung, I hope they're not replicate
Well,
too much.
yeah. Oh, so right. These are cancer cells.
Okay.
That's an important thing to say.
Yeah.
And the context in which we're doing this is a system in the lung, actually, but it's lung cancer. It's in cells that are in one state called the adeno state. And here they become another state that's called the squamous state. So we know that if we give this particular drug called adagrasib, whatever, they undergo this transition. And we suspect that it's by this pool change. Okay, so now what's my worst idea given this context?
Yes.
My worst idea is that we would be able to overcome the lack of individual cell resolution using this method, because one prediction is that there should be a reduction of variability, where at the beginning, according to our model, every cell could have different pools, but then one pool should win out. So we expect...
Wouldn't you expect that in the adeno state, variability is low, and then as you have adaptation, it would increase and then decrease again?
That's right. Exactly. Before we give the drug, it should be low. Essentially, every time there's a learning process, we expect variability. If there's
Yes.
learning without variability in the AP1 pool, we are wrong. And we're willing to accept that we're wrong, looking for a situation where we expect that cellular learning is happening, but there's no increase in cell pool variability.
Well, no increase is not something you'll be able to show, right? You
Yeah.
can only, the most you can say is that you don't see a change in variability, right? So are you sure that there should be a big change in variability? Like, do you know what the size of that change should be?
I actually don't. It's a bit of a,
So I don't think you can really rule out that you're right.
oh, but then it's not a killer experiment. We need
No.
a killer experiment.
But if you see the expected variation, right, then
It's
that's a support of your hypothesis.
The hypothesis gets to live another day.
Yes. Can you somehow quantify how much variation there should be?
Well, that's what this method would allow us to do, because at every state it would ask, what's the
No, it
budget?
would tell you what it is, but
What it
could you predict ahead of time what it should be if you're right?
So we have a model, and I guess it could make a specific prediction. That's right. Yeah, and we do see at the beginning in our model, there's no variability. There's like a maximum variability, and then it goes back down.
Yes, but the height of the peak, you would have to figure out what you expect. You know,
Yeah.
if you see this shape,
Well,
you didn't disprove the idea.
right.
But if you don't see it,
Right.
it would be good to know how much would you have seen if it had been there.
Yeah. I mean, if it goes like this, I think that kills our idea. If it goes like this, that seriously kills the idea. So would you say that's a bold prediction that we expect this kind of, I mean, maybe it's not a bold prediction if it's consistent with actually many scenarios. And so it doesn't distinguish anything. I guess what we need is a competing hypothesis.
Yeah. Well, my point is, it is a bold prediction.
Mm.
It's just not a way to, well, depending on what you see, you might disprove your idea. Like you say, when you see this or you see this, you might disprove the idea, but you might just see a flat line.
I think a flat line disproves our idea.
I don't think so, because you don't know what increase in variability you expect. Maybe the increase is small. Maybe the adaptation happens slowly.
You know, let me tell you something else, actually. Another key part of the model is that every dimer gets stabilized by phosphorylations.
Yes.
And that's actually the mechanism for how this works. New dimers are introduced.
Yes.
Ones that are correlated with a decrease in stress get stabilized. We do, to some extent, have a way to measure whether there are these, what we think are stabilizing phosphorylations on the dimer. Okay, and so then the model would be that these phosphorylations, these stabilizings, okay, so if we now look at stabilization, it's a different kind of plot. The things would not be stable, like very low, and then the population pool should be stable, should have these marks.
And vice versa, right? In
And
the
the-
adeno state, there should be some that are stable that become unstable as you
Right.
progress. Right? You should see both.
Well, in the adeno, we don't actually expect, because the cells don't have a problem. And so,
Yeah, but they have to be in a certain program.
yeah,
So you're
but
saying,
in a steady state, this is not used. This is
Okay.
our model is that this meta program called AP1 is only deployed upon stress to reduce stress. Once reduction of stress has happened, it's stabilized by other factors and they're no longer needed. And so here, pre-drug,
okay.
it shouldn't be there. So
Okay.
does that help us make a prediction?
Well, shouldn't that mean that there is not only low variability, but just no AP1 at all at the beginning?
Right. There should be no AP1 at all.
And is that something that people know?
See, look, that's what I said here. There's no AP1, and then it comes up. Remember,
No.
we said it here.
No, I thought that's variability.
I mean, there's no variability because they don't exist.
Yeah, but that's not what this plot. You didn't label the axis, but I thought the axis label was variability.
Oh yeah, I didn't label the axis, but that's what I meant.
Well,
Not labeling the
what,
axis is a tremendous strategy.
yeah, but what is the label on this axis?
Variability. No, it's I guess variability, and it's zero if they're not present.
Yeah, it could be zero because everyone's the same,
Yeah.
or it could be zero because they're not present.
Right. Yeah. So
Wouldn't
that's why.
wouldn't you also expect that the absolute number
Yeah. Yeah.
um,
Absolute
would
number.
then go down again at some point?
Yes.
Okay,
Once
so the
then
plot
this gets
for
stabilized. Yeah.
yeah, so they should look similar, the two
So it's
plots.
like, yeah, the plot is that there should be phosphorylations that are correlated with like the stability, the hey, we've learned,
Hmm.
and then the model predicts, although this is not a very like a crucial part of the model, but maybe we can say it, is that at a certain point, another mechanism takes over. But now, my crazy idea on this front is let's make two predictions. What does it look like for the stabilizing
Hmm.
dimers versus what does it look like for the unstable? So I think the unstable ones should look like this. You know, they come up. The stable ones come later. The system needs to figure it out that they're stable. Yeah, this is a prediction, right?
That's a
I,
prediction that some population that'll actually most should look like this, and only a subpopulation should look like that.
yes.
That's a strong prediction, I think. And here you should really see something, right? The variability.
Hmm.
I mean, that kind of is also a map of the variability because
Yeah.
here the variability will be low and here it will be high at that
Oh my
point.
God. Thank you for helping with this. Seriously.
I'm not sure how much I help.